So what is it?
So what is the black hole?
What is it? Yeah.
A black hole is a region of space. It's a region of space where the gravitational field is so strong that you can never leave that region of space to go to the outside world.
Jesus.
That's what it is. But, so Stephen Hawking, so there's different sort of levels of sophistication in thinking about what black holes are. So one level is to forget about quantum mechanics entirely. Use general relativity, Einstein's theory of gravity that he invented 100 years ago, 1916. And he says, what is gravity? It's space-time curving on itself. That's what gravity is. And he has equations to tell you how much space-time curves, etc. So we can describe black holes in those terms. And one of the things you find is that black holes only ever increase in size, right? They can suck things in, but they never shrink because they just suck things in.
Right.
But then in the 1970s, Stephen Hawking says, well, what if we take into account quantum mechanics? There are, there's these clouds of probability all around the black hole. And he says, if I look at a black hole, does it look completely black? And the answer is, to his great surprise, and still to ours, no, it doesn't look completely black. Even black holes, when you look at them, will be seen to gradually emit photons, to emit radiation very, very, very slowly.
And how are you looking at them? Like, what method are you using?
This is a thought experiment. We've never seen this in the real world. The actual black holes we know about emit radiation so slowly that there's no practical way to actually observe it. So this is entirely theoretical right now.
So, but if it is entirely theoretical, how do you measure that they're not entirely black?
We haven't been able to do that. We predict that they're not entirely black, but we've never verified that prediction yet.
You're freaking me out, man.
Yeah. Well, there's a lot of physics is making predictions that we can't yet test, but someday we're hoping.
But why even assume that? I mean, I don't understand what the motivation for assuming that they're not entirely black is.
It's not an assumption. It is if you believe what we think is already true about general relativity, the curvature of space-time, and quantum mechanics, then Hawking says it follows from those assumptions that black holes are not completely black. They give off radiation.
Okay.
Dark matter is real. It exists.
Yes.
Okay.
How do we measure it?
We measure its gravitational force.
Okay.
It pushes things around in the universe.
So what do we think it is?
We don't know. That's the thing. We know certain things about it. We know that it's dark. We know how much of it there is. It's about 5 times as much mass in dark matter than there is in ordinary matter. Ordinary matter is every particle we've ever seen ever, right? So all the atoms, all the stars, all the galaxies that we see in our telescopes, that's 5% of the mass. And then dark matter is 25%, and dark energy, which is something completely different, is the other 70% of the universe. And those are facts. That's basically 99% likely to be true. What it is, the dark matter, the dark energy, that is much more up in the air. We have lots of candidates, and we're not sure which one is right.
What was the initial discovery that led to the conclusion that dark matter is the preeminent mass of the universe? Like
Caltech predecessor Fritz Zwicky, famous astrophysicist, back in the 1930s, pointed out that galaxies were orbiting each other too fast in what are called clusters of galaxies. You look out there in the sky, you see like these bunches of galaxies that are orbiting each other. You calculate how heavy the galaxies should be from what you see. You can calculate using Newtonian laws of physics how fast they should be orbiting. They're actually orbiting much faster. And he said the only way for that to happen is if they're much more massive than you thought. If there's much more mass in there. There's some missing mass, okay? But at the time, we didn't know it could just be stars that we didn't see, or gas, or dust, or whatever. It wasn't really till the 1970s that Vera Rubin, a famous astrophysicist, looked at how individual galaxies are rotating. And she found that it's a similar kind of thing. The edges of the galaxies are moving way faster than they should be, given the amount of matter that is inside. and she concluded that there's a lot of dark matter causing a gravitational pull that we didn't see, but is causing the edges of the galaxies to spin a lot faster than they should be.
Does dark matter exist on Earth, or is it only in deep space?
It depends on what the right theory of dark matter is, but
okay.
in most theories, there are dark matter particles passing through your body right now.
Terrence McGetta had a fucking hilarious way of describing it. I'll do a terrible job of butchering it, but that people like this. It's funny how he was talking about how many scientists are atheists, that they don't want to believe in God. They don't want to, and he was an atheist as well. He was an atheist rather as well. But he said, but they do want you to believe that everything came out of nothing for no reason that anybody knows of 14 billion years ago. That there was this infinitely small area that was smaller than the head of a pin, and that's everything you see in the sky, and it exploded 14 billion years ago, and no one knows why.
That's right, yes. Good.
But isn't that I mean, that is so crazy. And, you know, it's one of those things that theists, you know, people that are really into gods and religion, they point to, like, well, this is the scientist's God. This is this event. This is a miracle. I mean, why do we think it happened?
Well, what is the reason? The evidence we have?
Yeah, like what is the current theory as to what the Big Bang, like why did the Big Bang take place?
Well, that's a good question. So there's no preferred conventional answer. We just don't know. That's not a we don't know because we're not sure. That's a we have no idea is the answer.